Am I? Yes, I'm back. Okay. So we're going to get started with our post-coffee break sessions. And could you join me in welcoming Kirill Pimenov for DHT, BFT, OMG.
Hey guys, come closer, especially those of you who are not necessarily computer science engineers. I think I will be aiming more on you because this way I will be able to make most impact with this talk. And yeah, this is called DHT, BFT, OMG, Know Your Building Blocks for Decentralized Applications. And this is a slight revision on top of a talk I did a year ago on the Web3 Summit conference. I believe it became better in the meantime, but it's you to decide. Yeah, my name is Kirill, and I work for Parity Technologies, and we are building the open source decentralized applications, and we managed to do that in a commercially profitable manner. And first thing I draw on those really nice handwritten slides is this, and this is what you see in any computer science book ever printed, because this is how computing looked in the 70s. And when computer science was started as a field, everything looked like that. There was a really expensive one, filling the full rooms of the computing center mainframe, which is the computer, and then you have just cheap dumb terminals around it, and you interact with that central mainframe, and basically this is what you are programming for. You are programming the mainframe to properly show the info on the terminals of the users, maybe in the concurrent fashion. And you know how computing looks now? You'll be surprised. And the only difference I actually noticed when drawing that is the screens now are much easier to draw. And this is ridiculous because basically all the clients in this picture are much more performant than the mainframe on the previous one. But because you are taught to build your systems, to structure your systems, to build the algorithms and principles, as on the previous slide, you end up combining your really wonderful, distributed, super powerful computing grid in a way which is maybe not necessarily efficient. But it tends to just reflect what you see, because if you only have a hammer, everything looks like a nail. So my point with this talk is just to present you as many non-hammers as possible, and then see if you can apply the, basically recognize those tasks and the tools for those tasks, which will allow you to reason about systems and say, oh, that can be easily decentralized. It can be easily built in a fashion that all the peers are on the equal level and there is no centralized company which controls everything. And this is especially important since recently, because in the end we start as a humanity to come to realization that centralization and centralized control is a liability. It is not only of course, it's not so pleasant to be client on this picture, because then you don't have any rights and you are on basically given in under total control of the cloud company, which will be all the brands you recognize. But it's other way around a little bit, being that company is also not the most pleasant business in existence, because you more and more have to deal with a constant nagging of people in the client's space or in the higher level in the governance space, looking at you and saying, oh, you have a control, we want you to do X. And that X sometimes unreasonable, and not only from the business perspective, but from the actual, the losing the baby with the water sort of fashion, trying to suppress certain unwanted speech, and okay, we as a government want you to implement censorship, and we as consumers who don't think that much ahead, and we also want you to implement the censorship, and you end up trying to figure out, okay, I'm a WhatsApp and I'm sort of decent encrypted messenger, and now I need to do censorship on those encrypted messages. It's not the easiest and nicest spot to be at. But if you wouldn't be Facebook, if you wouldn't be that huge block in the center which has all the total control over the system, you wouldn't be in this place anymore. And you can just design the system with the freedom of all the peers ingrained in the way you design it. And I believe this is the right thing to do. So if you can, go ahead. And I'm just going to give you toolkit to do that. Yeah, this is the most famous picture of all computer science books probably ever. And it tells us that there are more or less 3 categories of systems, but more and more we look at the last 2 pictures, more and more we see that they're actually not that different. And I will try to make distinction between decentralized and distributed systems, but I will sleep all the time, and everyone I know sleeps all the time, because basically the distinction there is not that huge. There is a huge boundary between centralized and decentralized, and this is more or less 0 to 1 sort of distinction. But between decentralized and distributed, distinction is not that high, because actually not all the peers are equal in any network. That's sort of like how all the heterogeneous networks work. You have smartphones, and you have always powered on desktop towers, and you have laptops, and those are they interact with system differently. So is it still you get ideally distributed system, and you have some peers constantly online, and some peers are only going online, then they need some info, and you get sort of decentralized system, because you cannot rely on those transient peers. But does it change things a lot? No, I don't think so. But having or not having the centralized source of truth changes game significantly. So, yeah, what makes so hard? Why we tend to build centralized systems? What are the easy things for us to build in a centralized way, which tries to steer the whole engineering in that direction? Yeah, I said that we probably read more about them in the books, and then we tend to replicate what we read instead of going on the building block shopping. Yeah, I know how to solve it in one way, so I will solve it in my way instead of looking for another. But there are other differences we will have to deal with every time we build decentralized system. And coordination problems is the most obvious, most blatant, most widely encountered problem of decentralized systems. And they are explicitly it's really easy to coordinate single node. If someone has control over a single node and they do whatever they want, that's the end of coordination problem. But not unlike systems composed of humans, if we have multiple nodes who are more or less equal, it requires certain informational exchange and negotiation to get to certain developments in those systems. And for example, yeah, no singular source of truth, and one node is telling me one thing, another node is telling me another thing. How do I reconcile those? How do I build some coherent worldview out of it? It is not unlike looking at the diverse media and figuring out what is true and what is not. And you also see how in the human scenarios, we want a ministry of truth. We want someone who label the news for us. This is fake news, this is not fake news. But then you see how we try to solve this problem with centralization even in the naturally decentralized scenarios. And this is why it's so tempting for the naturally centralized scenarios of computer science as well. But I believe we can do better. Both as humanity and as a software engineering community, we can do better than that. I will probably show you how. No global clock, that's surprising. It sounds like a small thing. It's okay, who cares about time in those systems? I have my clock, it's fine, I will just trusting it. Unfortunately, you cannot believe how much of a semantics in your language depends on clock. And this is I work in distributed systems, and I work in security for distributed systems. And I read a lot of papers and proposals. We will solve this decentralized problem by this and this and this. And then you basically reading their language, you notice that they have implicit understanding of the node which came up earlier will be the winning one, or something like that, which is, yeah, it implies centralized clock. And no, you don't have that. So you need to think better. You need to figure out something smarter. And yeah, you cannot even build a centralized clock on top of a properly decentralized system. Randomness, that's just a very engineering angle of problem, but that's also the very fair angle of problem. Since you don't have a single source of truth, You cannot just trust random node on the net to tell you, yes, 42 is a random number guaranteed by a random dice throw. You need to be smarter about that, and there is no like one-size-fits-all way. And surprisingly, a lot of algorithms in computer science, they depend, oh, we pick a node by random, and when you figure yourself in the position that you cannot do that, it changes the game a lot. And yeah, complicated protocol upgrades, that's once again the question of human structures on top of our systems and democracy and how governance works. But like you probably have at least somehow seen how Bitcoin updates flopped, because it is a really hard coordination problems. How do you make all the nodes on the system to agree, like using the old protocol to agree explicitly on a new protocol and then move to it? And like, what do you do with dissenting opinion? This is, once again, we are at a really nice point then our engineering problems start resembling the real life political problems. And it is going to be funnier and funnier over years. Please, like, yeah, bear with the field and try to do some good. Like, yeah, another obvious problem, like probably everyone heard about that, as a Byzantine fault tolerance. Like, you cannot tell apart node which failed and node which is malicious. If some of you played multiplayer games, you know those guys who disconnect instead of conceding in the matches. You can never tell, is it like the ISP failure, or is it failure of an actual like a player who decided that it's more preferable for them to do this. And yeah, this is like sort of what you see in the decentralized networks a lot, especially if there is some human value in those systems. And you need to design the systems to be Byzantine fault tolerant, like to be able to tolerate that behavior you cannot point finger to and say, yeah, this is malicious. Some behaviors are clearly malicious. You cannot make that by accident, but like trying to forge digital signature is obvious. Like, yeah, it doesn't match. You are trying to feed me disinformation. That's clear. But there are things which are not, and it is like, it requires some reasoning about systems. That's what makes it complicated. And yeah, like you want the systems where you don't control membership. And this is also a very novel problem, because if you've ever heard about like all the ridiculous conversations about identity on the blockchain and so on, it's like, we don't like that problem. We try to avoid having it, and instead we want to handle passports like in the real life, but in a digital world, it's probably a bad and oppressive measure. I'm not going to tell it's not oppressive in the real world, but like, yeah, identity is a mechanism of control. It probably originates from a single entity. And if we are talking about more fair, more democratic, more inclusive institutions in the digital world, then we cannot have like identities, and then like, yeah, anyone can join as many times as they can, and you need to build a system which doesn't make an assumption that one node is one person and doesn't like make voting depending on the amount of like fake sock puppets you put on the net and so on. This is, by the way, even a problem for the centralized institutions, like, and Facebook and other platforms, they try to present themselves as a solution to this membership problem, but yeah, it is not. And if you ever will look at the literature on the decentralized systems, you will see that like sock puppets as a Sybil attack. And yeah, like basically it's sock puppets you have to fight on Twitter. It's like not more complicated than that. Don't be like put off by a really scary and not very clear term in there. So, toolkit, what it is, like what can you use to solve particular problems in a decentralized, fair, permissionless way. And yeah, I even made, yeah, you have other things than a hammer in there. That's the important point for me. So yeah, first thing is encryption. Like I just need to talk about that because this is the foundation of everything else. Because with a centralized system, like in some sense, it's really forgiving. Because as long as you have a control, you can always revert like bad decisions. Like you can, someone hacks in your account, you can always like take back the commands later, or like you can just delete the hacked account or do something. In the decentralized account systems, you cannot just do that. There is no centralized authority, so you need to build informational security system as a part of your protocol. And basically, encryption is the foundation of that. And the only thing you all need to know is that there exist two different kinds of encryption. One is called symmetric, and this is like when I have a password and I encrypt things with a password, and then I use the same password to retrieve info back. And if I want to share the info with someone else, I will tell them the password. And that has a very clear benefit. It's easy to understand, it's easy to encode, and it's actually quite fast. Like, it is at least faster than you can transmit bytes of the network, so it works perfectly for our decentralized like internet-based systems. But it has a huge drawback of like, how do I transfer the secret, like the password? And then there is asymmetric encryption, which is a little bit arcane-ish. It uses things which are called like different complicated names, like elliptic curves, or like discrete logarithm problems, and so on. And they work, and we are sure they work pretty well, and they're damn slow. If you are really being smart in implementing them, they're still like 10,000 times slower than encrypting the same thing with just AES, which is like you go to symmetric cipher. Not that you should use AES anywhere. We have Chachapoly, but like just saying. So what you're doing is like you have your random password for symmetric encryption, you encrypt that asymmetrically, and you pass it around. And then, yeah, I must probably explain a little bit in pictures what asymmetric encryption is and how it works if it doesn't have passwords. And like, you can imagine the mailbox where anyone can put mail inside, but only the owner of a key can open it and retrieve it. And this is basically how encryption in asymmetric format works. You have two keys. One is called public key, and it is basically known by everyone. And you have private key, which is only known by you. And then anyone who knows the public key can put things in your encrypted mailbox, and only you with your private key can open it and extract things. So when you are doing any practical application of encryption, you use asymmetric encryption to establish the session key. Basically, you create a random, unique password, and you put it into that mailbox, and the receiving end opens it and reads it, and no one in the middle can intercept it or extract it. And then you use that random password to just facilitate the symmetric encryption, and this is how you actually exchange information. And this is pretty widespread. When you see that green padlock in the corner of your browser, this is exactly what happens when you establish the communication with the server. But like, yeah, you don't need to have that server-client relationships to use these primitives. Another point of asymmetric encryption, you can use it other way around. You can make a mailbox when only you can put things inside, but everyone else can read them. And that's called digital signatures. And you probably encountered them in real life, like being mentioned and being relied upon. But you need to understand that it's even like the same key pair. You can use your private key to sign things, and then everyone can use your public key to verify things. It is exactly the same mathematical procedure, just turned upside down. Yeah, and this is consensus protocols. So like, as we talked about not having a single coordinator, not having a single source of truth, you need to have smarter mechanisms of getting to the consensus. Like, you need to make all nodes to have a certain rule set to figure out what is true, what is like correct at the certain moment. And we actually managed to figure out a lot of different, like slightly different protocols to figure that out. And like the most known maybe for the general audience would be proof of work, when basically whoever in a fixed amount of time finds the lottery ticket with a like most beautiful number by some abstract metric, like you just draw random numbers and you see if it's beautiful or not. And then you all reveal them at the end of a round, and whoever has the most beautiful is the source of truth. And we can guarantee that those are random. Like, a person winning on one round doesn't have any benefit on winning on any next round. And this is basically how proof of work works. It is incredibly computationally intensive and wasteful, and yeah, we can do better, and we do research to do better, and we are going, like we at Parity are going to launch networks which are much better in providing you the consensus protocols, like by the end of the year or beginning next one. Please follow the Polkadot project. But you basically, you need to understand that you cannot do that on any decision. So instead, you are using that for the thing which is called leader election, which is basically, yeah, we want to have our micro Facebook for the next 5 seconds. And that will be the lottery winner. And then we will take the lottery once again, and we will pick up the next leader, and so on. And because those leaders are randomly distributed across all the participating peers, we believe that they will never collude and they will never do the coordinated malicious actions. And if they'll do just random malicious actions, I don't care. For example, if you heard about like transacting on the Bitcoin, then yeah, every individual block author, like the miner, can censor your transactions. They say, oh yeah, I won't be including the transactions from that guy. He looks like a really unpleasant guy. I'm not going to include them in the block. But you don't care because the next or the next after next doesn't have the same presupposition against you. So you will have your transaction be there eventually. And that it makes no sense for the first person to censor you at the first time because they are not getting anything because your transactions will get into the system anyway. So yeah, we are not using consensus protocols to make every decision on the network, but instead we are just electing the leaders for a certain time frame, and then those leaders are working. We believe that they will be much more just than just having a leader forever and trusting Facebook to be good to us. Yeah, there are two different kinds of protocols here. The proof of work is important because it's asynchronous, it assumes that all the networks can be, all the nodes mining Bitcoin can be disconnected from the internet most of the time. It is a nice property. Unfortunately, sometimes it's better to sacrifice that and require the nodes to be connected to the internet to exchange messages with another if you can not waste the Iceland worth of energy for mining. So currently the major research is how do we make partially synchronous consensus protocols? How do we make protocols where nodes actually talk to each other to figure out what the election outcome, lottery outcome is? But how do we not make that too consuming? Because you don't want to put in disadvantage nodes on the shitty 3G connection, for example. You want to include them, but if the messages are lost, if they are just slower to ping, then how not to make them disadvantaged. And this is the challenge of building the synchronous, semi-synchronous consensus protocols. I think we're doing well enough, but we'll see how it develops in the next couple of years. You just need to know that, yeah, there are consensus protocols. Even if you have a lot of random, equally valuable peers, you can apply certain algorithms to figure out what is the global truth in such system is. Oh yeah, content-based addressing is really small but powerful idea. If you've ever seen a dead link on the internet, you know that the files go down because domains expire or the whole domain zones expire. There have been certain domain zones with domains assigned which has been decommissioned because, for example, Czechoslovakia had been split in Czechia and Slovakia. And obviously all the resources which were on the previous domain zone, they're no longer reachable. And that's a problem of naming the references, no matter what is the scheme you put to name things, to point them in the global computing cloud, which informational atmosphere we have around our planet. If those are arbitrary human readable names, unfortunately they will expire because meaning of different semantical categories in our language changes over time. So you cannot just trust arbitrary human understandable identifiers to be persistent. And that's a huge problem. I want to be able to read Wikipedia in 100 years, but probably the naming scheme they have in there is not ideal for one reason or another. And we don't know now what is the problem with that. So the solution is called content-based addressing. And it is about let us take the content, the file itself, and make the derivative of that its address. Basically, the easiest way you can do hash, and you call that hash the unique identifier of the file. And that gives you a superpower. If you are, in 100 years, there will be definitely the media archaeology as a mainstream field. Even more, I know that there is at least one media archaeologist right now in the audience. But it will be much more mainstream in 100 years. So you dig up a file from the broken link on the internet, and you hash it, and you get exactly the same address as it was when it was first uploaded. So you don't depend on file being online as long as it is somewhere. And that's a really nice property. And this is like things like BitTorrent work like that, but also like there are a couple of people from the IPFS project in the audience. And this is how IPFS works exactly for this reason. We want those links to describe what's inside. Not how people decide to name it, but what it truly is. Because then mutually like different and set aside parties will definitely agree on what that link leads to. Yeah, and this is the next thing, like, okay, I'm the new node in the network, how do I figure out who I talk to? And like, yeah, obviously you can just go to the bootstrap node, which is like the same as the centralized authority. It is like, yeah, we use Facebook, but we only use Facebook to start up our application. And you see how well it works for Tor. In China, Tor is blocked exactly by this way. Like you start your Tor client for the first time and you go to the authorized directory services to get the list of the Tor nodes. And if you block those directories, okay, your Tor doesn't work because you don't know who to talk in the huge network. You cannot just go to random addresses the same way as you cannot go to the random doors finding for your friend in a new town, right? So there are a couple of mechanisms which exist which simplifies this problem. They don't solve it at all, but they simplify it to a certain degree. And the first one is like local network, local algorithms. Basically, you cannot ask everyone, but you can ask some small section of everyone. And it is surprisingly helpful because it is more often than not, the computers in the same local network do the same task at the same time. Very easy example, people doing the computer science workshop. They all sort of work on the same problem, and like making them, helping them, starting exchange information on that problem will make it so much easier. The most straightforward thing is like you work on the web front end and you download something from NPM, and that's a lot of files, and we all know how slow it is. If you put that on something like, if you will allow peers to discover each other and exchange that content, you will speed up that like orders of magnitude, because everyone in the same computer class will be doing the same, and they will be not bound by the small, slow, outbound channel to talk about that. Then there is an important thing which is called distributed hash table. That's really the discovery mechanism in the network right now. It uses both to discover peers and to discover the content. For example, if you've ever seen Bitcoin magnet links, they work exactly like that. They basically, all Bitcoin peers in the network have some small chunks of what Bitcoin torrents, BitTorrent torrents, in which allocated on which peers. And then you just ask, but you ask in a particular way. Basically, you look at what your address is, and you look at the nodes, and you try to map like the nodes which names are mostly reflecting the content. Basically, it's as if you will try to find your friend John on the John Street. But you agree that everyone on the John Street has a registry of everyone who named John in the town. Like they not mandated to live on the John Street, but they mandated to tell to the John Streets where they live actually. And this is how DHT works. And then, like once again, we can make assumptions of nodes talking to each other continuously, and there is a thing which is called gossiping, which is basically I'm not asking about peers, but I'm telling, oh look, I found my friend, he's called John. If anyone else is interested, here is his address. And you exchange that over the network, and you can do that in a scalable and secure way. And those are like rather nice, rather interesting protocols which allow you to do that. So basically, if you start up a new node in the peer-to-peer network, there are multiple ways for you to figure out who else is on that network, who else has the info on that network you're interested in particular, and generally you maintain the connectivity, so you never end up being a lone, scared node in the darkness again. Yeah, those are things with scary names. They are called conflict-free replicated data types, and they are also called operational transformations. It is a discussional topic if those are the same or just logically equivalent, whatever that is. But it's an important thing to know, I'm on the street counting pedestrians on the sidewalk because I want to know how many people are passing there per hour because I want to open my shawarma place somewhere. And I ask my friend to do the same. And I'm a little bit distracted some of the time, and my friend is distracted some of the time. The question is like, how do we get accurate number by joining two inaccurate numbers? And that's the big problem because we don't know if we have been distracted at the same time or not. We cannot just sum up our numbers. It will make no sense. We will double count a lot of people. So instead of doing that, we will do something like, okay, blonde girl, really tall, red shoes, 1. And then we will try to merge those records, and we will merge only those records which are not matching to each other. And this is why it's called conflict-free, because you can always merge them, and you will get the info which is meaningful. And you've seen that, actually. If you co-work on the Google Docs, this is what you're using. You're using CRDT, like you're typing letters in one place, another person is typing letters on another place, and then you, bam, and you have a joint Google Doc. And that's basically using that stack. So let's play with that. Let's try to compose computing systems out of that, because like bricks are fine, but we are not here to study the computer science. We are here to build systems to change the world. So yeah, file sharing network, like what do we need to? Obviously, like we need content-based addressing because we want that content to be discoverable regardless if it's called wonderful movie with capital letters or not. So we don't want to be dependent on the computer names. So we go for content-based addressing for the content. And then we have peer discovery because you need to figure out whom to talk about that content. And content discovery because you need to figure out who actually has that content in the end. And if you think that this is only good for torrents, think again, just you can really, like you don't need Facebook to exchange photos or blog posts. You don't need centralized services for that. It's basically files to be shared. And the only reason you do that with Facebook is, as I said, it is because this is what we started learning computer science as a humanity with. Peer-to-peer messaging. Like, I don't want Facebook to read my messages. The easiest way to do that is not to give Facebook my messages. I want to give messages to my wife because I'm sending message to her. And yeah, that's asymmetric encryption. I want them to be encrypted. I don't want anyone, when I pass around my message, I don't want anyone to read it. And peer discovery, like I sort of know who that go to, and if we're in the same peer-to-peer network, I just need to figure out on, like, is she on the Starbucks Wi-Fi, is she at home where she is, what is her IP address, and as soon as I figure it out, I can send my message, which is encrypted. Easy, very useful. If you think about it, Tor is also peer-to-peer messaging. You figure out whom you need to talk to in order to get to this protected resource or something like that. Just you have several layers of protected messaging, but that's not hard to understand how to do that. Yeah, distributed ledger, it's called blockchain, and everyone thinks that it's about money. It's like wrong, because like just money is the easiest thing you can use ledger to keep track of, but you can use it for much more useful things eventually. But like it's asymmetric encryption again. I want to be the only one to transact with my money, or I want to be the only one who can like declare certain things on my name. So I will digitally sign them, so I need asymmetric encryption for that. And then everyone else can say, yeah, that guy is actually university who can certify degrees, and he certified this and this and this, but he never certified the degree that guy is a fraud. So yeah, you need asymmetric encryption for that. And you need to do peer discovery, and in the end you need consensus protocol, because you need to agree on what is the global state of things in here. This, yeah, it's probably easy to understand. Like, you don't need to understand how all of those pieces work, but like you can assemble them and you get something meaningful. And yeah, collaborative editor, Google Docs can be reasonably decentralized. And yeah, you need CRDTs, you have asymmetric encryption to have authorships, because you want probably to only accept the corrections from the people you trust, and so on. And you need peer discovery to figure out where those people are. And you get a rather decent Google Docs, which doesn't require a server to run. And yeah, let's decentralize Facebook. You just mix all of them. Like, that's it. It is like collaborative editor for the comments and file sharing network for the uploading pictures of cats. That is what Facebook is. It's basically you get those 5 building blocks, you match them together. And then it takes maybe a decade of UX engineering to make it to the point where like everyone likes to use it, but that's a completely separate area. Like you need to understand that it's possible, and this is like achievable with technology we have now. We don't need to wait for breakthroughs. Yeah, let's talk about like very briefly about other building blocks, just for you recognizing the names and recognizing the problems. Yeah, routing protocols. We talked about mesh networking yesterday. This is it. We cannot always rely that all the peers on the network can directly talk to each other. There are some of people in China and they're behind Chinese firewall. We want to be able to pass messages to them, so we need to figure out the way to break through the firewalls. Or someone is on the, I don't know, ham radio in the disaster-stricken region. We want them to still be the part of a huge peer-to-peer network, and we don't want, like, basically we cannot trust the centralized infrastructure we have now to be always resilient. So there are routing protocols which exist. They're like mostly called mesh networks, and you can build them and you can use them to provide you communication fabric for your peer-to-peer networks. Verifiable randomness functions. Basically, the problem with generating randomness in the distributed system is actually solved by things which are called like this. I probably don't have enough time to explain how they work, but they exist. You can Google them up. Distributed secret generation and sharing. That's actually quite interesting because this is something which is so counterintuitive. You like probably I will need to explain how they work, but think about it. You can tell 3 friends of you a secret in a way that any 2 of them know the secret if we join together, but individual person doesn't know anything about that. It's not like they know half a secret, they know 0 of a secret. We can do that, and like if you imagine, for example, the curve, like the cubic parabola, and you can like pick 3 points on it, and any 3 points on the cubic parabola, they identify the cubic parabola uniquely. But any 2 points on the cubic parabola, they don't give you any information of how it works. So like basically there is infinite possibilities to draw the third order curve over 2 points, but there is only one way to draw a third order polynomial over 3 points. So this is how you require 3 people to gather together to recover the secret, because your curve can encode it in a way. Threshold signatures, yeah, you can, like when you rely on people signing things, and you have tens of thousands of them, it is very not practical to verify tens of thousands of signatures because, as we remember, asymmetric encryption is terribly slow. So threshold signatures are the signatures where you can just join them together. And they will end up in the really, really, really tiny signature, which is easy to verify, but it verifies that at least half of those 10,000 people have signed this message. Yeah, you can see how it becomes more and more quantum mechanics-like, and now we are coming to the really things which are quantum mechanics of computer algorithms, in the sense that you cannot internalize them. You cannot understand them with a common sense. It's fine. Everyone is in the same shoes as you. You can only use math and logical reasoning to learn about them, and zero-knowledge proofs are one of those things. It's basically, I can create a package of info which will verify to you that I know a certain secret without revealing to you anything about that secret. Think of that in a way. I have a deck of cards, and I take one card and I tell you that I have a red card. And I don't want to reveal to you which red card of 13, or like how many of them, I don't know, I don't play cards. So which of the cards is in there, I don't want to reveal that. But how do I prove that it's indeed red? I take other cards, all the black ones, and I show them to you. And it's enough for you to count them and verify that yeah, they're all unique black cards. So what you have remaining is a red card, but you haven't told me which. And zero-knowledge proofs are basically that. I can form the informational package which proves a certain statement. For example, yeah, at the moment of this transaction, I had enough money on my account without revealing you how much money I had there. And this is surprisingly useful. And yeah, homomorphic encryption is a really thing which is like even more scary than that. But imagine you can encrypt data and then it's gibberish. But then you can search in the data and get a meaningful result. It's not possible. But with homomorphic encryption, it sort of is possible. You can encrypt your query in a special way, and then you can ask other peers to apply encrypted query to encrypted data to end up with encrypted result, which you get back and you decrypt it, and that's the answer to the question you asked about the data you have never disclosed to other parties. That's surprising, that's terrifying, that's really, really, really slow, and we're speaking about like 100 times slower than the slowest computer on Earth. Like really, it can do like maybe 100 of computations per second. But it is surprisingly useful, and this is like the building block, and I believe a lot of systems in the future will be relying on it. Yeah, go and build something amazing. And yeah, it's not a medical advice. Contradictions and side effects exist. Please consult your local cryptographician before implementing your own crypto. Thank you. Do we have time for questions?
We have time for a couple questions, and we'll have a roving mic if you wanna. If anyone has burning questions, I see some already. I'll hand over mine.
Thanks. So, well, I actually have two, but if you have time just for one, it's okay. The most important thing I'm looking at, and how do you share the public key? Because before it was like common sense, okay, we just publish it somewhere where everyone knows and it works. Well, recently we discovered, take PGP public key servers. They were attacked. Somebody put hundreds of thousands additional keys there, and it actually makes them malfunction. So we were assuming it worked. It worked for 2 decades probably, or what time? Anyways, at least for a decade. Now it doesn't. So, and its main question, when you use asymmetric encryption, its main question, how do you share this public key without relying on a third party? Because if you have
I got the question. Maybe I can.
And if you'll have second one, the future, because decentralized systems are good. You mentioned PC, laptop, phone. PC is nice for decentralized, especially with wide IP, but we're getting less and less PCs produced. People are moving towards cell phones, which are locked in provider network under carrier-grade net, and IPv6 is probably will not kick in, or even if it will be blocked for inbound connections in many areas. So in the future, how are we going? Because it's easy when you have a server.
I think I can get both of the questions. I can start answering and save a little bit of time. So the first question, like the answer is surprisingly, yeah, we can have a consensus protocol to decide consensus on what public keys are legit. Like it is a implementation detail, which particular consensus protocol we pick and what guarantees it will provide. We can design a lot of different systems. The easiest, the most stupidest thing is to just put the messages signed by those keys on the blockchain, and then you can always say, yeah, actually that person who claims to be that actually controls that key. And then you use the consensus mechanism, which is given to you by the public ledger, by blockchain, to verify that, there is all the keys people wanted to put in there, they're actually up there and they're searchable. And this brings us to the second part of the question, how do we work, how do we live in a world where more and more people are only transiently online? And the answer is that we add some incentivization to the game. So probably it will be better for you on some level or another, but to run node, laptop, always connected, or the desktop, or even a dedicated server. And I believe we see a success in the systems like that with different, you can pay people some sort of internet money for keeping nodes online. That's what Bitcoin does, for example. If you keep your miner online, you get rewarded for processing transactions. Or you can just incentivize them on a social level, and this is what Secure Scuttlebutt is doing. There are servers which are just meeting points for people to communicate. And people are doing that for certain internet fame and fuzzy feeling, and it scales pretty well, surprisingly. So yeah, I don't see that we will end up in a dystopian world where only large corporations are allowed to run the always online services. And if it's not the case, we can always solve the problem of who I talk to in decentralized system.
We're just a little over time, so we might want to wrap that up.
Sure.
Could you join me in giving Kirill a round of applause?
I'm wearing this t-shirt. You will recognize me. Come and talk to me.
Yeah, and so I'm sure if you have extra questions, Kirill will be happy to answer them. We're going to do a short turnover, and maybe this is another moment